Hi, I welcome you all to this session where we are going to learn about the first experimental proof which occurred way back in the early 20th century to prove that light or radiation does behave as particles. And that experimental proof is called as the Compton Effect. Taking you along on this journey is Dr. Eunice Jerusha, an assistant professor of physics. Light as radiation was widely accepted to be that of a wave, but in 1923, Arthur H. Compton, a physicist, studied the light-matter interaction and completely changed the way in which people viewed light. And he said that light could be considered as particles, and in 1927 he received a Nobel Prize for this discovery. Based on the quantum theory of radiation, we know that the exchange of energy between the light radiation and particle is discrete in nature. Therefore, based on this, let us see what the definition of a photon is. A photon is defined as a discrete energy value in the form of small packets or bundles or quanta of definite frequency or wavelength which propagate with the speed of light as a particle. These photons therefore are quite similar to that of electrons, and they have certain definite quantities such as the speed with which they move, which is c, and the wavelength of light, lambda. Light can be considered to be made up of particles called as photons, and these photons have a different kind of characteristic or properties compared to that of electrons. Let us see what they are. Light, which is electromagnetic radiation, consists of these photons which are zero rest mass particles and they travel at the speed of light. Photons are completely electrically neutral and therefore they cannot be deflected by electric as well as magnetic fields. Also, since they are chargeless, they do not ionize any material. Also, since photons are electromagnetic radiation particles, they possess an energy E which is equal to h nu. And using Einstein's energy mass relationship, we have E to be equal to mc square, and therefore the momentum of this photon is given by mc, which is equal to h by lambda. Therefore, Compton effect can be defined as when a beam of high frequency radiation from an X-ray or a gamma ray is scattered by a substance of low atomic number such as carbon, the scattered radiations consist of two components. One has the same wavelength as that of the original incident ray and the other has a slightly longer wavelength. The phenomenon of this change in wavelength of the scattered rays is called as Compton shift, and the effect is known as Compton effect. As a result of Compton effect, there is a scattering which takes place, and this scattering results in the presence of two types of radiation. One is called as the unmodified radiation and the other is called as the modified radiation. There is a difference in the wavelength of the unmodified and modified radiation which results in what is called as the Compton shift. Compton shift therefore is when a photon of energy h nu collides with an electron of a scatterer at rest, the photon gives its energy to the electron. The scattered photon will have less energy or a higher wavelength, lambda prime, compared to the incident photon which has a higher energy or lower wavelength, lambda. and the electron in turn gains energy by recoiling with a velocity v. This shift in wavelength or change in wavelength is what is termed as Compton shift. In order to proceed with the theory behind Compton effect, one needs to know the principle behind this phenomenon. The principle is the collision between an electron and a photon is considered, and using the laws of conservation of energy and momentum, the expression for the Compton wavelength is obtained. Here we see the Compton effect, where we have the collision between the high energy beam of X-rays or gamma rays with an electron which is present in a scatterer of a low atomic number. And during this elastic collision, the photons lose energy whereas the electron gains energy, and thereby the photons move away due to scattering with a lesser energy and thereby a higher wavelength, whereas the electron, which was originally at rest, gains energy and recoils and moves out with a higher energy. Some of the assumptions made for Compton effect to occur are: the collision occurs between the photon and an electron at rest which is present in the scattering material. The electron is free and is at rest before collision with the incident photon. And there is no loss in energy during collision, that is, an elastic collision occurs between the gamma rays and the electrons which are present in the scatterer. As a result, the photons which are originally in the radiation having wave-like nature turn out to be particles possessing particle-like nature. With these assumptions in mind, let us consider a photon of energy h nu which collides with an electron at rest, and let us assume that this electron at rest possesses an energy m naught c square, where m naught is the rest mass of the electron. During this collision process, a part of the energy is given to the electron, which in turn increases in its kinetic energy, and hence it recoils at an angle phi and moves away with a kinetic energy mc square. The scattered photon, on the other hand, gets scattered at an angle theta and moves away with a small amount of energy h nu prime with respect to the original direction. Now, let us now proceed to find the energy of the system before and after collision. The energy of the system before collision involves the two particles, the incident photon and the electron at rest. Therefore, the energy of the incident photon is h nu, the energy of the electron at rest is m naught c square, and the total energy therefore before collision is a sum of these two energies, which is h nu plus m naught c square. We call this equation as equation A. Now, for the energy of the system after collision. Here, the particles involved are the scattered photon and the recoiled electron. The energy of the scattered photon is given by h nu prime. The energy of the recoiled electron is mc square, and therefore, the total energy after collision is h nu prime plus mc square. This equation we represent as equation B. And now, using the law of conservation of energy, the energy before collision must be equal to the energy after collision, and therefore, we equate equation A and B, and we obtain h nu plus m naught c square to be equal to h nu prime plus mc square, which we denote by equation 1. We now proceed to find the momentum of the particles which are involved in this elastic collision process called as the Compton effect. The particles which are present before the collision are the incident photon and the electron at rest. Both these particles are moving only in the x direction and therefore their contribution to the momentum is only from the x direction alone. The momentum of the incident photon is given by h nu by c and the momentum of the electron which is at rest is 0. Moving on to the after collision process, the particles which are present here are the scattered photon and the recoil electron. The scattered photon and the recoil electron move in the xy plane and therefore their individual momenta have to be resolved into the x and y components. The scattered photons momentum is given by h nu prime by c. The x component of the scattered photons momentum is h nu prime by c cos theta and its y component of the momentum is h nu prime by c sin theta. This scattered photon has a scattering angle given by theta. For the recoil electron, the momentum is mv. The x component of the momentum for this recoil electron is mv cos phi and the corresponding y component of the momentum is minus mv sin phi, phi being the recoil angle of the recoil electron. We now write in the form of statements the momentum of the various particles which are involved in the collision process and assign equation numbers to them. Firstly, we start with the momentum of the system before collision. Along the x direction, we have the incident photon and the electron at rest in movement. Therefore, the momentum of the incident photon is h nu by c and the momentum of the electron at rest is 0. And hence, the total momentum of these two particles before collision is h nu by c and we call this to be equation C. Along the y-axis, we have the contribution of these two particles to be 0 since they move only along the x direction and therefore the total momentum before collision along the y direction is 0 and we call this to be equation D. Looking at the momentum of the system after collision, we have the two particles, the scattered photon and the recoil electron. Let us look at their contributions to the x direction. The momentum of the scattered photon is given by h nu prime by c cos theta and the momentum of the recoil electron is mv cos phi. Hence, the total momentum after collision along the x direction is h nu prime by c cos theta plus mv cos phi, which we denote by equation E. For the y direction, the momentum of the scattered photon is h nu prime by c sin theta and the momentum of the recoil electron is minus mv sin phi. Therefore, the total momentum after collision along the y direction is h nu prime by c sin theta minus mv sin phi, to which we assign equation F. Based on the law of conservation of momentum, we have the momenta along the x direction to be equated and we have h nu by c to be equal to h nu prime by c cos theta plus mv cos phi. This we represent as equation 2. For the y direction, we equate equation D and equation F and we have this expression 0 is equal to h nu prime by c sin theta minus mv sin phi, which we represent as equation 3. The table shown here is a compilation of all the energy and momenta of the particles which are involved before collision and the particles which are involved after collision. And we have used the law of conservation of energy and the law of conservation of momentum, and we have obtained equations 1, 2 and 3. We now have to process these three equations further and find what is the Compton shift. We use equation 1 and we have mc squared to be equal to h into nu minus nu prime plus m naught c square, which we term as equation 4. We square this equation 4 and we have m square c power 4 to be equal to h into nu minus nu prime plus m naught c square the whole square. Expanding, using the common expression a plus b the whole square to be equal to a square plus b square plus 2ab, we have m square c power 4 to be equal to h square into nu minus nu prime square plus m naught square c power 4 plus 2h nu minus nu prime m naught c square. The first term needs to be expanded further using the expression a minus b the whole square equals a square plus b square minus 2ab, and we have equation 5 therefore to be m square c power 4 equals h square into nu square plus nu prime square minus 2 nu prime plus m naught square c power 4 plus 2h nu minus nu prime m naught c square. We use equation 2 now, which is mv cos phi equals h nu by c minus h nu prime by c cos theta. Taking the common term h by c out, we have h by c into nu minus nu prime cos theta. We take c to the LHS. We have therefore mv c cos phi to be equal to h into nu minus nu prime cos theta, which we call as equation 6. We now square this equation 6 and we have m square v square c square cos square phi equals h square into nu square plus nu prime square cos square theta minus 2 nu prime cos theta. We have used the common expression here a minus b the whole square. Using this particular expansion version, we have m square v square c square cos square phi to be equal to h square nu square plus h square nu prime square cos square theta minus 2h square nu prime cos theta. We call this to be equation 7. We use equation 3 now, which is mv sin phi equals h nu prime by c sin theta. Taking c to the LHS, we have mvc sin phi to be equal to h nu prime sin theta, which we call as equation 8. Squaring this, we have m square v square c square sin square phi equals h square nu prime square sin square theta, which we represent as equation 9. We now add equations 7 and 9 and rearrange the various terms thus obtained in this manner. We have therefore m square v square c square to be equal to h square nu square plus h square nu prime square minus 2h square nu prime cos theta. We represent this as equation 10. This equation 10 is now to be subtracted from the earlier obtained equation 5. On subtraction, we have m square c square into c square minus v square equals m naught square c power 4 plus 2h nu minus nu prime m naught c square minus 2h square nu prime into 1 minus cos theta. This we call as equation 11. Using the theory of relativity and especially the relativistic mass of the electron, we have m to be equal to m naught divided by square root 1 minus v square by c square. we square either side of this equation, we take the LCM and do a small cross multiplication to obtain m naught square c square equals m square into c square minus v square. We multiply either side of this equation by c square. We therefore have m naught square c power 4 to be equal to m square c square into c square minus v square. This we call as equation 12. We now compare equation 12 with equation 11 and we have 2h into nu minus nu prime m naught c square equals 2h square nu prime into 1 minus cos theta. Cancellation of 2h on either side gives us nu minus nu prime m naught c square equals h nu prime into 1 minus cos theta. We now do a small cross multiplication taking nu prime which is there on the RHS to the LHS and m naught c square which is present in the LHS is taken to the RHS. Next, we divide each term which is there on the LHS with nu prime. We have therefore 1 by nu prime minus 1 by nu to be equal to h by m naught c square into 1 minus cos theta. On multiplication of either side with c, the velocity of light, we have c by nu prime minus c by nu to be equal to h by m naught c into 1 minus cos theta. We know that c by nu prime is lambda prime and c by nu is lambda. Therefore, the Compton shift is lambda prime minus lambda equals delta lambda, where delta lambda is equal to h by m naught c into 1 minus cos theta. This we represent as equation 13. The wavelength of the scattered photon lambda prime is given by therefore lambda prime equals lambda plus h by m naught c into 1 minus cos theta, which is equation 14. Therefore, it is clearly seen that some amount of the incident photon energy is lost during the elastic collision with the electron which was at rest. We now go in for some special cases where we substitute various values for the scattering angle theta and find what the Compton shift is. In the first case, we substitute theta to be equal to 0. Therefore, cos theta or cos 0 is equal to 1, making the Compton shift to be equal to 0. This clearly implies that scattering had never occurred and that the outcoming radiation has the same wavelength as that of the incident radiation. Therefore, at the output, we obtain just a single peak. In case 2, we assume theta, the scattering angle, to be equal to 90 degrees, thereby making cos 90 to be equal to 0. When we substitute this cos theta to be 0 in equation 13, we have the Compton shift to be equal to h by m naught c. On substitution of the various values of h, m naught and c, we obtain the Compton shift to be 0.02424 angstrom. This value of the Compton shift is called as the Compton wavelength and is in very good agreement with the experimental results. For case 3, when the angle of scattering is 180 degrees, cos theta turns out to be -1 and therefore the Compton shift delta lambda is 2h by m naught c, and on substitution of the various terms, we have the Compton shift delta lambda as 0.04848 angstrom. It is found that when theta is at a maximum of 180 degrees, the shift in wavelength is also maximum. Therefore, from the above cases, it is clearly observed that the shift in wavelength increases only with respect to the scattering angle. When the angle of scattering varies from 0 degrees to 180 degrees, the wavelength shifts from lambda to lambda plus 2h by m naught c. And from the intensity curves which we observe for various scattering angles, it is seen that when theta is 0 degrees, we have a single peak, and with an increasing value of the scattering angle, the shift in wavelength between the incident wavelength and that of the scattered wavelength increases. In order to experimentally verify that Compton effect does occur with a shift in wavelength during the collision between the photon and the electron, we have an experimental setup. And from the experimental setup, we go ahead and see the working of the setup and find out and prove that Compton effect does occur. The experimental setup is as follows. It consists of an X-ray tube for producing X-rays. A small block of carbon is mounted on a circular table as shown in the figure. A Bragg spectrometer BS is allowed to swing freely in an arc above the scattering element to catch the scattered photons. Slits S1 and S2 help to focus the X-rays onto the scattering element. X-rays of monochromatic wavelength lambda is produced from the X-ray tube. These are made to pass through the slits S1 and S2. These X-rays are next made to fall on the scattering element which is present on the circular table. The scattered X-rays are received with the help of the Bragg spectrometer and the scattered wavelength is measured. This experiment is repeated for various scattering angles and the scattered wavelengths are measured. The experimental results are plotted. From the figure shown, the scattering angle theta equal to 0 degrees, the scattered radiation peak will be the same as that of the incident radiation peak A. Now, when the scattering angle is increased for one incident radiation peak A of wavelength lambda, we get two scattered peaks A and B. Here, the peak A is found to be of the same wavelength as that of the incident wavelength, and the peak B is of a greater wavelength than the incident radiation. The shift in wavelength or difference in wavelength delta lambda of the two scattered beams is found to increase with respect to increase in the scattering angle. At theta equal to 90 degrees, the delta lambda value is found to be 0.0236 angstrom, which is in good agreement with the theoretical results. Hence, this wavelength is called as the Compton wavelength and the shift in wavelength is called as the Compton shift. Thus, Compton effect was a visible proof that high frequency radiation such as X-rays or gamma rays, which were originally thought to have wave nature, now exist in the form of particles and undergo interaction with other particles. In this session, you would have obtained the expression for the Compton shift as well as the wavelength of the scattered radiation. Thank you for your patient listening.